Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab simulations can transform your teaching approach, making lessons more interactive and captivating for your students. Scholar Lab is a distinctive 3D virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. Let's explore an exciting chemistry simulation focused on extracting metals from their ores based on their reactivity. Let me open extraction of metal simulation for you. Let's start with the game plan or objective of this simulation, which is to explore and understand various extraction and refining processes to extract and purify metals from their naturally occurring ores. If you are a new user, I would recommend you to go through this section thoroughly to understand the simulation and to enhance your teaching practices. Let me close this game plan. This simulation covers three main categories of metals based on their reactivity: low reactivity, medium reactivity or moderate reactivity, and high reactivity. Each category uses different extraction techniques. Let's begin by exploring these techniques step by step. Before getting into this, I would like to share few words about the simulation. You can use your mouse button by click, drag, or you can use this icon over here in the bottom right corner to view the laboratory conditions in 4 different angles: T for top, F for front, R for right, and L for left. And also you can make use of this magnifying tool to zoom in and zoom out the experiments. Let's start with the low reactivity metals. Here we have gold, silver, mercury, and copper. Low reactivity metals like gold and silver occur in their native state. We can extract them through electro-refining. Let's do it for gold. Here I am having an electrolytic solution, which is dilute HCl with gold or platinum. As a cathode, I took pure gold, and as an anode, I took impure gold. Let me immerse these electrodes to the electrolytic solution. By inserting the key, I am giving the power supply to electro-refining process. As you can see on the board, the anodic and cathodic reactions are thoroughly written in the board to teach them clearly. And use the zoom in feature here to understand how the ions are transforming from anode to cathode, how the pure gold is getting deposited to the cathode and the impurities are getting deposited under anode. Similar kind of experiment can be performed with silver as well. Let me quickly show that to you. Here I am having silver nitrate along with dilute HNO3 as an electrolytic solution and cathode and anode as pure silver and impure silver respectively. As you can see, the silver is getting deposited on cathode and the impurities are collected as an anode mud. Let's go to the next part, which is mercury. Mercury is more reactive when we are comparing that with gold or silver. For that, we have to do roasting before proceeding to electrolytic refining or thermal decomposition. For that, let me take this ceramic dish and put it on the burner. I'm using cinnabar as an ore for mercury, which is mercuric sulfide. By clicking on it, I'm adding ore to the ceramic dish. By the way, I am turning off this labeling by using this tag button over here so that the reaction on the board is clearly visible now. And as the reaction proceeds, it is giving us the pungent smell. It's because of mercuric sulfide along with oxygen and heat, it is producing mercuric oxide and sulfur dioxide. I'm turning off the stove by clicking on it. After that, we can proceed with thermal decomposition for the refining of mercury oxide. I'm turning on the Bunsen. As you can see, the produced mercuric oxide, by heating, it is giving us mercury as a liquid along with oxygen. So which is collected in the conical flask here. Using this slider, you can increase or decrease the burner capacity. As a fourth part of low reactivity metals, I have copper. Like mercury, copper is also more reactive than silver and gold. We have to do roasting for copper. Here the copper ore I have taken, that is copper sulfide. By clicking on it, it will get added to the ceramic dish. Let me switch on the burner to start the process. As you can see, it is producing sulfur dioxide with a pungent smell, and by giving the extra heat, it is producing copper. I'm using the glass rod to mix it well so that each and every part of the ore is getting heated and for producing the copper as a metal. Once the process is done, we have to go to electro refining to get purified copper. By clicking on electro refining, it will give you the setup of copper sulfate solution along with some electrodes. Copper sulfate as an electrolytic solution used here, and pure and impure copper taken as a cathode and anode respectively. I am clicking on key to add the power supply to the container, and the anode and cathode reactions are given here. As you can see, the impure copper is getting depleted and the pure copper is getting deposited on the cathode side. Once the reaction is over, you can clearly see that anodic and cathodic reactions had happened over there. As the next part of the simulation, let me show moderate reactivity metals to you. Under moderate reactivity metals, we can't proceed through electro refining first because they are getting it as a combined state, not as a native state. So here we have lead, zinc and manganese. And also for a moderately reactive metals, we have two types of processes. One is roasting, another one is calcination. For roasting, we must use sulfide ore, and for calcination, we are using carbonate ore. We have given two options over here in the bottom. You can select accordingly. For sulfide ore, we used galena, PBS, and as a carbonate ore, we used lead carbonate. Let me go with galena first. I'm clicking on the ceramic dish to start the process of roasting. I'm adding galena to the ceramic dish. Clicking on the Bunsen to get that started. As you can see, lead sulfide with oxygen and heat, it is producing lead oxide and carbon dioxide. Once the reaction or the roasting process is over, we can proceed with carbon reduction. For that, we are using coke powder. I am mixing coke powder with lead oxide by using the glass rod. As you can see, lead oxide with carbon, it is producing lead with carbon monoxide. Then the lead can be purified using electrolytic refining. You can proceed with the similar experiment for refining lead. Let me go to zinc and show you for carbonate ore, calcination part. For that, we took zinc calamine, which is zinc carbonate, as an ore of zinc. As we all know, roasting have to happen in the presence of air, and the calcination for the carbonate ore have to be happen in the absence of air or the limited supply of air. So for that, we are using the lid to protect the air affecting the zinc calamine. Once the calcination is over, we can proceed to carbon reduction. For that, we are adding coke powder by clicking on it. And I'm using glass rod to get that mixed. Side by side, you can get the view of the reaction, what is happening over there in the extraction process. Once the zinc got concentrated, we can proceed to electrolytic refining by clicking on it and start the process to extract the pure zinc metal. Here I am using zinc sulfide as an electrolytic solution. You can conduct a very similar electrolytic refining for zinc as well. Let me proceed to manganese. Manganese, unlike lead and zinc, here we are taking displacement reaction because that is more reactive when we are compared with other two metals under moderately reactive elements. For that, I'm taking ceramic dish. I'm using manganese dioxide For the displacement, I took aluminium powder to react with manganese dioxide. Let me mix it thoroughly so that the aluminium powder can displace manganese dioxide. As you can see, manganese dioxide with aluminium, it is producing manganese along with aluminium trioxide, aluminium oxide with heat. Once the displacement reaction is over, you can proceed to electrolytic refining now. For that, we are using manganese sulfate as electrolytic solution, and as usual, pure manganese and impure manganese is taken in cathode and anode part. Let me take you through the third part, which is high reactivity metals. In this part, undeniably, we have to talk about sodium, because this sodium extraction can't be done in our school laboratory. It needs a industrial equipment to do this process, because we are using a high temperature furnace to carry on this experiment. So the furnace setup is given over here, and I'm adding sodium chloride to the furnace to get that melted. Let me close this furnace and switching on it. Once it is getting melted, we are going to check the temperature of the furnace and let's see how much it is getting melted. For that, I am clicking on thermometer to measure the temperature. It's 820 now. Now you can click on the furnace to view how the sodium chloride are getting molted and how we are proceeding through the reaction. For that, let me close the lid and place the beaker beaker is used to collect the sodium as a molted state. As you can see, anode and cathode reactions are given in the board. To see what is anode and what is cathode, you can click on this button over here to view which is acting as an anode and which is acting as a cathode. Here, graphite is acting as anode and the cathode is iron. Let me take you through the last part of the simulation, that is quiz. In the quiz, we are having set of 5 questions to understand how well the students understood the concept and where they are lagging in knowledge. Here, you have to attempt all 5 questions to check the marks. You can click on check answers to see what are the answers are correct or incorrect. And also you can click on explanation to view what is the explanation of the incorrect answer and for correct answer as well. Hope you got a clear idea about how these simulations will be enhancing your teaching practices, as well as how the students will understand the concept better using these kind of simulations. Happy learning. Thank you for watching.